Hello. All right. This is a good moment for me, I think. I'm excited to see if I can get through this video, because if I can implement this last piece of the train function in the neural network library, then I'll have a working version of some kind of neural network library-like thing that I can start to finally apply to some projects. And it's my goal, actually, that in some of the future videos I make that make use of the library and eventually other more sophisticated machine learning and deep learning libraries like deeplearn.js, and a new library, which I think is now going to be called ML5, which I'll talk about in another video, that I'll be able, really what I'm excited about is to make stuff and show you how to make stuff. But I'm kind of working through this because it's just something I have to do. So I started, I have to finish. I'm just trying to like vamp till you stop, move on, and watch something else, because I'm not sure you should continue. So, but let me try to, since it's actually been a while since I recorded the previous video, unfortunately I might be watching them one after another, let me try to like reset kind of where I think that we are. So we have something like a two-layer network. It has, an input, quote-unquote, air quote layer. It has so these are the inputs. This is the hidden, and this is the output. It is fully connected, meaning every input is connected to every hidden, and every output is connected to every hidden is connected to every input, every output is connected to every hidden, and so the outputs come out here, the inputs come out here. All of these connections have a weight, and we can consider them in a weight matrix, and I guess I should put this stuff back in here. Weight, if this is like input 1, 2, 3, this is hidden 1, 2, this is weight 1 to 1, this is weight 2 to 1, so these all end up in a nice weight matrix. These end up in a weight matrix. The outputs come out, oh boy, in an array, like y1, y2, a vector. The inputs come in a vector x1, x2, x3. Okay, I'm getting back into this. I didn't even draw like off the top. Wonderful. So now, the idea is we want to do training, and the kind of training that I'm doing right now is called supervised learning, where I have some known inputs with known outputs, inputs with target outputs. I send the inputs in, I feed them forward, I get some actual guess output back, and I have some sort of error, which we can think of as the error equals the guess, the guess minus the target. So I'm going to say like y minus target. Okay? So this is the error. Now, I should have mentioned before that there are a variety of ways to train a neural network. And by training, I mean adjusting all of these weights like they're knobs to try to actually get the matched target output when you send in the training data. So one thing I should mention, I really got to even just take a minute to make a video just about this. But in most training situations, you'll have training data, test data, and then of course, there's the actual unknown data. So we want to say like, oh, here's some labeled data. I'm going to use that to train. But I need to save some of that labeled data, because what if I train my neural network only to work with the training data, but it doesn't actually work with any other data? Well, I can determine that by giving it some data that I didn't train it with, but I know the answer to see how it does with that. And that's how we can evaluate it. So I just wanted to mention that. This is going to be the process. Now, this idea of backpropagation with gradient descent is one technique, and it's a technique, I'll put some links in this video's description. You can read about the history of it. It's been around for a long time. It's a big innovation in training neural networks. But there is a lot of questions as to whether that's optimal, best for the future, et cetera. There's different slight tweaks of these algorithms. And I actually, next, probably after I get through this, plan to use a genetic algorithm to evolve the weights of a neural network, which opens up the door for a lot of kinds of projects that I'm excited to try to make. So all that aside, here we are. What did we get so far? We figured out in the previous video, we calculated this error, and then we calculated the hidden error, which I'll just call H error. Right? That's part of backpropagation. It's, well, we have this error. How do we distribute this error all around so we can adjust all these weights? The reason why we're doing this is because we actually did this already twice. I've done this twice. Once with, if you look at my videos about a single perceptron, right? Which gets 2 inputs. I forgot about the bias. I can never remember the bias. I am biased against the bias. I'll come back to that. But the single perceptron, which just takes in 2 inputs and 1 output, well, it doesn't have to take, it's a single neuron. It can take in more than 2 inputs, but a single neuron with multiple inputs and an output. I actually did this. We did this idea of training this with gradient descent. And we also did it, I did it in a video about linear regression, where if I have a bunch of points in a 2-dimensional space, I can find the line that fits these points the best. And I did this. What's interesting here is, though, so first of all, linear regression, if you recall, there's actually a mathematical formula to just compute the exact line of best fit. It's called ordinary least squares. I think I went through that in the previous video as well. But the idea here, and so the idea here is we're trying to figure out y equals mx plus b, the formula for this line. Well, basically, what this is doing is this is exactly the same process that we needed here, only we have these weights. You can almost think of this as like M and this is B maybe or something if there's just one input and a bias. We had to fit all the stuff coming through here into a line. Well, this is actually what we need to do with all of these places, right? We basically need to do the exact same algorithm that we did for this one line to compute. This is the weight and this is the bias. What we really have, right, is not y equals mx plus b. We have y equals m1x1 plus m2x2 plus m3, can you see that? x3 plus m4x4, blah, 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 plus b. We basically have exactly the same problem, but in a multi-dimensional space. So I just need to figure out how do I adjust each one of these, m1, m2, m3, m4, and b, all of these weights inside of the matrix. So the same training method I did for linear regression, gradient descent, the same thing we did with the perceptron, we now need to apply it here in this multi-dimensional space. So what should I do next? Now, first of all, I forgot to thank a bunch of the resources. Hold on. Some viewers rightly pointed out that when I did this previously, and I guess the convention is target minus y. The nice thing about this is if you look at a cost function for a machine learning system, you'll see that the cost function is the sum of all the errors squared. So if you do target minus y or y minus target and you square it, doesn't really matter. But it is an important distinction probably. You have to get it right, of course. Otherwise, you might start training in the wrong direction, as you'll start to see as we do other stuff. OK. Let me come over here and let me thank. So I'm going to come back to this video in a second. But let me first say there are 3 things. One is this is a new resource that just came. Well, it's not a new resource, but a new page on the ML4A, ml4a.github.io site. This is a site put together by Gene Kogan. It has a ton of machine learning resources, videos, examples, demos, et cetera. It's amazing. And there is a nice article here about how neural networks are trained with a lot more detail than I'm going to get into here. But you can see the same sort of idea of talking about linear regression, a loss function, adding more dimensions. This is the idea. This is what we're doing. Of course, I highly recommend you watch the 3 Blue 1 Brown series about gradient descent, backpropagation, and backpropagation calculus. This will give you a massive, extreme set background for what I'm going to attempt to do. It's just kind of like, let me just type this in code, like kind of squint, and then press a button and hope it works. So this is great. I highly recommend this. And then I also have been using the Make Your Own Neural Network book, which I could hold up and wave around for you, by Tariq Rashid. And there's a link to it on the Coding Train Amazon shop, along with some other books that I've been using for videos. And then, so this is where what I wanted to do now is try to connect back to here. This is from my previous video entitled The Mathematics of Gradient Descent, where I go through a long algorithm to arrive at a very simple result, which is in this case of y equals mx plus b, what I'm looking to do is calculate the change in m and the change in b. And so we can now write those formulas over here. So in the case of y equals mx plus b, we need to calculate delta m. How do we want m to change based on the error? And how we want m to change is the learning rate. By the way, learning rate, if you look in textbooks and stuff, is sometimes written with this, the Greek letter alpha, I believe. Is that alpha? Yeah. Learning rate times x times error. And delta b equals learning rate times error. This is all done through some calculus in looking at the cost function, looking at the derivative of the cost function, the slope, and how to walk around that cost function and find the bottom, the minimum error. What values of m and b do we have to have the minimum error? And that's what we want to do here. What values of w11, w21, w31, w41, w51, blah, 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 have to have the minimum error? And that error, each individual error, we've got to like back it up and pass it around and chop it up. Okay, so how do we take this and move this to a multi-dimensional scenario? I'm going to rewrite these a little smaller further over to the left so I have more room to write out the formulas for the matrix version. Okay, so these are the formulas for the change in slope and change in by offset. Change in m and change in b for y equals mx plus b. So I have the same situation, except I have a slightly different one. I have like the output equals sigma of like that whole, weight matrix. What is it? Matrix product with the, I guess it's with the inputs, right? I have this kind of formula. This is basically the same thing plus the bias. Plus the bias, which is a vector. So I have basically the same thing, but instead of like single dimension, these are all matrices, multi-dimensional. So what I'm going to attempt to do now is I'm going to just write out a notation for these formulas using matrices and try to compare and contrast a little bit. And I'm not sure if I'm going to get it right because I'm using a combination of trying to keep consistent with my notation from before and some conventions. But let's see, I've got it written down here. Let's look at this. So let's first just say I just want to figure out delta for these weights. So in other words, you can think of what I'm doing is instead of just delta m, I want all of these weights. So I want to say delta, all of the weights, and the weights are from hidden to output. The change in each weight, I, j, each row I, column j, I think that's what I've been using. It's hard for me to remember what I used in the last video. Equals, and this is going to look very similar. First of all, learning rate, same, always have the learning rate. Learning rate's going to basically tune how big of a step are we going to take. And I don't like the way, I kind of want to rewrite this just because to have it match the way I'm going to write the matrix version. Error times x. I'm going to write this times the vector e, right? That's the vector of output 1 minus target 1, output 2, or target 1 minus output 1, right? That error vector that I've talked about. And then x in this case is kind of like the input to this neuron, to each of this output layer. So I'm going to call that, in this form, I'm going to call that I could call it x, but I'm going to call it h. It's what's coming out of the hidden layer. I'm going to put that here. I'm going to put that at the end, h. So these are the components that exactly match up here, times h. Right? We have learning rate. We have the error, right? And by the way, if I were doing this for this layer, if I would say delta w weights from I to j from input to hidden, I, h, would equal the learning rate. And then I would say times the hidden error. Right? Do you remember that from the previous videos where I went through how to get the output error and the hidden error, how we pass all that around? And then this is times the input. So this is the same exact formula, but two different layers. Learning rate, errors, or hidden errors, the hidden output, or the input output. It's sort of weird to say the hidden output. The hidden output is the input to the output. The input is the input to the hidden. So you can sort of see how this formula is looking at this part, and this formula is looking at this part. Okay. But I didn't put one other thing in here. There's something funny that's going to go in this spot right here. So what goes here? This is the question. Now this is where we're so happy to have this book, Make Your Own Neural Network, because we can just look up the formula in here. But what actually is going to go here is the derivative of the output. Now let's think about this. Why am I coming up with derivatives? You might have remembered back from the mathematics of gradient descent that we had to take the derivative. But in this case of y, in this case, it's mx plus b. It's a very simple derivative. It's a linear function. Here we have this sigmoid thing. We need to calculate the gradient. And the gradient is the error of the output times the derivative of the output. How does the output change? How does the output change relative to the errors? So in this case, right, we need to add in here the derivative of sigmoid. Now here's the wonderful thing. Sigmoid is the function, right? The derivative of sigmoid, s prime x, is simply equal to the sigmoid of x times 1 minus, can you see what I'm writing? Yes, sigmoid of x. So in this case, we need to calculate this gradient, the derivative of sigmoid. And right here, now one thing I should really clarify here is, so learning rate is a scalar number. Error is a vector. Learning rate is a scalar number. I'm going to put an asterisk here. A hidden error is a vector. So I need to multiply, and the output is a vector. So these are actually, this is element-wise multiplication of the what's coming out of here, out of output, has already had the sigmoid pass through it. So I just need to say the output plus 1 minus the output. The output plus 1 minus the output. Now, what's weird about this is now the h is really this, right? We have the exact same formula. I have the learning rate, the error, the gradient here. You can sort of consider this. The gradient here is just the error. The gradient here is the error times the derivative of the output. And then if I'm multiplying, I need to get a weight matrix. So the input, by the way, is also a vector, but I need to get a matrix. So the interesting thing that happens, if I use the matrix product here and transpose this vector, right? This is element-wise multiplication. This is just a scalar. Now, here's the thing. If I have if I have this error and time, the gradient essentially, I'll call it gradient, as a single column vector, 4 columns, if I multiply that by the hidden output, which is also a single column vector but transposed, if you take a single column matrix and multiply it by a single row matrix, as long as this has the same number of columns as this has rows, let's look at what happens, right? There's a wonderful website that I use often when I get stuck. It's called matrixmultiplication.xyz. And here what I can do is I'm going to make this exact, right? Here's an arbitrary single column vector. And then I'm going to make a single row vector. So a 1 column matrix, a 1 row matrix. I'm going to hit multiply. So this is, I'm just going to go to the end here. This is a nice little animation that goes through everything that I did in previous matrix multiplications. And you can see we end up with a 4 by 4 matrix. So this is exactly what we need to do to be able to get the deltas for all the weights. Okay, so this also has to be, if I'm going here, this has to be transposed, and this should be element-wise multiplication with I lost track here. So I'm taking the output error and multiplied by the derivative of the output. Here I'm taking the hidden error and multiplying it by the derivative of the hidden. So that would be h plus 1. So not plus. Ooh, what I have plus here? I've had that wrong for so long. Times. That's another element-wise multiplication. Times 1, and this is a 1, not an I. 1 minus h. Okay, I think we've done it. I'm going to just check here my trusty guide that I highly recommend that you read instead of listening to me. And I'm going to look at this. The change in weight matrix equals learning rate times the error times sigmoid of the output. Well, I have sigmoid kind of built in here. I'm assuming the output at the sigmoid has already been done. Times 1 minus sigmoid of the output. I'm assuming sigmoid has already been done. With the dot product or the matrix multiplication of the hidden, the output transpose. Well, this is right. My notation is slightly different. Okay, so I think we're just about ready. Now, of course, I forgot about the bias. So I'm going to have to basically do exactly the same thing with the bias. The bias is always simpler. because I can just get rid of this. So I'm assuming I could probably sort of do the same thing here. So, but I'll get to that in a minute. Let me at least try to implement this in the code, and then and I'll do that in the next video, and then we'll come back to the bias.